talk about principal component analysis and why it shows up everywhere in Python and machine learning. Principal component analysis is a way to take a dataset that has lots of overlapping features and rewrite it with fewer features that capture the most meaningful parts of the data. The key idea of PCA is correlation. When two or more features are correlated, it means they tend to move together. When one goes up, the other goes up too, and vice versa. And if a dataset has lots of features that are strongly correlated, those variables are not providing any new information. They are partly describing the same underlying behavior in the data, and this causes unnecessary noise in the features, so PCA attempts to fix this. Imagine that you have a cloud of points in a scatter plot, except instead of just having two axes, you might have 10 or even 100. If you could rotate the coordinate system in any way you want, you could line up the first axis to point in the direction where all the points are as spread out as possible. This is the direction that contains the biggest pattern of variation in our data. The way PCA chooses this direction is by trying many different directions and asking the same question for each one. If I measure all of the points along this direction, are all of the points really spread out or bunched up? The best direction is where all of the points have the most possible variation, and PCA calls that the principal component. Once it picks that, it looks for the second direction that is perpendicular to the first one and captures the next biggest amount of variance that is still remaining. The reason it must be perpendicular to the first one is so that it describes a different pattern instead of accidentally pointing partly along the first direction again. And we keep repeating this process until you have as many components as you want. So these components are not your original columns, but a weighted combination of them. This means it is created by multiplying each individual feature by a certain weight and then adding them all together. These weights are chosen specifically so that each component measures as much variation in the data as possible, while of course being forced to measure different patterns from the components that came before it. Because of this, PCA produces components that are uncorrelated with each other, and this is extremely useful if you want to simplify modeling, compress the data, or visualize it without redundancy. Now, this concept of explaining variance is really central to the idea of PCA. If the principal component explains, say, 70% of the variance, then you will preserve 70% of the overall spread that you would have had with all of the original dimensions. But you lose that remaining 30% because you threw away all the other variation that lived in other directions. When people say PCA is a dimensionality reduction method, what they mean is that instead of keeping all of the components, you keep the few that measure most of the variance, and in return accept a controlled amount of information loss in exchange for a simpler representation. One detail that matters a lot in real life use is scaling. If you have one feature that's measured on a really big scale, like a person's annual income in dollars, and another feature that's measured on a smaller scale, like their age, the large scale feature can absolutely dominate the variance because of its units, not because it represents something important. And that is why PCA is always done after standardizing the features, which is when you subtract the mean and divide by the standard deviation for each feature. The output of PCA is usually described with two things. First is the transformed data. This is your dataset after PCA has rewritten it into the new coordinate system. You still have the same rows, but what actually changes is the columns. Instead of having the original feature columns, you now have columns named something like PC1, PC2, PC3, and so on. Each of these new columns is a principal component, and each row gets a score for each component. This score is just a number that tells you where that score lands along that component's direction. If a row has a high PC1 score, that means that observation strongly follows the main pattern PCA found in the data. If the score is low or even negative, it means that observation sits on the opposite side of that pattern. And this transformed data is what you might feed into your machine learning model instead of the original feature. And the second output is the loadings. The loading summarizes how each original feature contributes to a principal component and how strongly it influences it. By looking at which features have the largest loadings, you can understand what the component is capturing overall and describe it more clearly. There are also many important limitations to PCA that you should know so you don't use it in the wrong situation. PCA is a linear method, so it can only capture linear structures and will struggle a lot with strongly nonlinear structures, unless you use more advanced variants. PCA is also unsupervised, meaning it does not know or care about your target label at all. So the directions that explain the most variance are not necessarily going to be the directions that predict your target variable the best. And this is why sometimes PCA can even hurt your machine learning prediction. So here's an example in Python. The PCA takes your scaled feature set and finds a small number of new axes that capture the biggest overall pattern in how your data varies. Then it rewrites every row using the coordinates on those new axes. So each observation variation is represented by a few component scores instead of those many overlapping features. Along the way, it also tells you how much variation the code captures and the feature weights that tell you what each component is mostly made of. And that is a full breakdown of principal component analysis for you, so don't forget to save this video for the next time you're working with PCA and follow for more. See you in the next one.